2018. A British Airways Boeing 787 was towed to a remote stand at London Heathrow. It was covered with a maintenance tarp, then another, then a third. Across the world, similar scenes were playing out. 787s operated by Air New Zealand, Virgin Atlantic, and All Nippon Airways being pulled from service without warning. Not because of a crash, not because of a fire, because of a crack, a microscopic crack in a single turbine blade, smaller than a human fingernail. Hidden deep inside a Rolls-Royce Trent 1000 engine, an engine that had been certified as airworthy, that had passed every test rolls Royce's engineers had designed, and that was supposed to power the world's most advanced commercial aircraft for decades. By the time the full scale of the problem became clear, Rolls-Royce had grounded roughly 50 aircraft worldwide, racked up charges of £2.4 billion, and come within a board meeting of being nationalized by the British government. Here is the part that nobody talks about. The crack wasn't a surprise. Rolls-Royce knew that blade fatigue was a potential issue before the Trent 1000 entered service. They chose to manage it rather than fix it, and that choice almost brought down not just Rolls-Royce, but the 787 program, and with it, an entire generation of long-haul aviation. To understand how Rolls-Royce arrived at this disaster, you need to understand what the Trent 1000 was supposed to represent. By the mid-2000s, Rolls-Royce was fighting a very particular competitive battle. In the large commercial engine market, the company had spent decades as the perpetual third player, behind G and Pratt and Whitney in total market share, behind GE 90 in the ultra, high-thrust wide-body segment, and behind both rivals in the critical narrow-body market, where the CFM56 dominated. The Trent family, a series of three-shaft turbofan engines first introduced in 1995, was Rolls-Royce's bid to change that calculus. The Trent 800 had powered the Boeing 777. The Trent had been selected for the Airbus A. Boschy, and the Trent 1000 was Rolls-Royce's chance to own the 787. The aircraft that Boeing was promising would define the next 50 years of long-haul aviation. The 787 competition was brutal. GA entered with the Jenks, a proven architecture derived from the highly successful GA90. Rolls-Royce entered with the Trent 1000, a clean sheet design optimized specifically for the 787's requirements. When Boeing's customers made their selections, some choosing Jenks, some choosing Trent 1000, some offering a choice, Rolls-Royce secured roughly 40% of the 787 engine market. It was their most important commercial engine win in a generation. The Trent 1000 would power aircraft for airlines in Japan, the United Kingdom, Australia, New Zealand, and dozens of other markets. For Rolls-Royce, it was validation that the Trent architecture could compete at the highest level. But during development, a problem emerged that would not fully surface for another decade. The Trent 1000's intermediate pressure turbine blades, components that operate in extreme temperatures and at extreme rotational speeds, showed signs of premature fatigue in certain operating conditions. Specifically, the blade coatings were wearing in ways that allowed oxidation to begin earlier than the certification models predicted. This was a known phenomenon in turbine engineering. Blade degradation under thermal and mechanical stress was something every engine maker managed. The question was always how fast it happened, and whether it happened within the safe inspection intervals. Rolls-Royce's engineers determined that the degradation was manageable. They developed inspection protocols. They set maintenance intervals. They certified the engine with the Civil Aviation Authority and the FAA, disclosing the blade behavior and demonstrating that inspections would catch any dangerous deterioration before it became a safety issue. The regulators accepted this approach. The Trent 1000 entered commercial service in 2011, powering ANA's first 787 from Tokyo to Hong Kong. For the first several years, the inspection regime appeared to be working, but the real-world operating conditions that the 787 was flying. Longer routes, higher utilization rates, more thrust cycles per Dalton Y than the models had anticipated, were degrading the blades faster than the certification environment had predicted, and because the blade deterioration was primarily visible inside the engine, it wasn't something that a visual inspection during a regular maintenance stop would catch. It required borescope inspections of the engine interior, and those inspections were scheduled at the intervals Rolls-Royce had calculated, intervals that turned out to be too long. The first serious warning came in 2016, when in-service inspections began revealing blade cracking at a higher rate than expected. Rolls-Royce tightened the inspection intervals for a subset of engines. They did not ground aircraft. They did not make a public disclosure. They treated it as a maintenance management issue, which, technically, it was. The aircraft kept flying, but the problem was accelerating. By 2017, it was becoming clear that the original certification assumptions were significantly wrong. The blades were cracking faster and in more engines than Rolls-Royce's models had suggested. More critically, some of the cracking was occurring in ways that were not detectable at the scheduled inspection intervals, meaning there were engines in service that had cracks that nobody knew about. Rolls-Royce began issuing a series of airworthiness directives, each one tightening the inspection requirements, some of them mandating immediate inspections before the next flight. Airlines began discovering that aircraft they had scheduled to fly were not, in fact, cleared to fly. The operational chaos that followed was severe. Airlines running Trent 1000 powered 787 suddenly found themselves with aircraft on the ground pending inspections that required specialized equipment and Rolls-Royce technicians who were already overwhelmed. British Airways grounded multiple aircraft. Virgin Atlantic canceled routes. Air New Zealand flew passengers on replacement aircraft and absorbed millions in associated costs. Each tightened airworthiness directive triggered a new wave of groundings. At the peak of the crisis, in 2018 and 2019, Rolls-Royce had roughly 50 aircraft out of service simultaneously, a significant fraction of the global Trent 1,000 fleet. The financial consequences for Rolls-Royce were staggering. The company took charges of £554 million in 2017, then revised them upward repeatedly. By the time the crisis reached its full accounting reckoning, Rolls-Royce had booked £2.4 billion in charges related to the Trent 1,000 problem. This included the cost of inspecting every engine, replacing degraded blades, compensating airlines for lost revenue, and additional operating costs, and funding an accelerated development program to redesign the affected components. The redesigned Package B and Package C blades took years to certify and deploy across the fleet. The timing was catastrophic for the company. Rolls-Royce was simultaneously dealing with problems on its Trent 900. The Aviation engine, following an uncontained engine failure on a Qantas Abashi in Launceston, Yishur, that had nearly brought down the aircraft. It was managing the development of the Trent XWB for the AA, Wushu, and it was facing a broader civil aerospace downturn compounded by COVID-19, when the 787 crisis was still active. By 2020, Rolls-Royce's debt had ballooned to £5 billion. Its credit rating had been cut to junk. The company raised £2 billion in emergency equity and sold assets to avoid insolvency. The British government held discussions about potential intervention. What had started as a blade fatigue management issue had become an existential threat to one of Britain's most iconic industrial companies. The full investigation ultimately traced the root of the problem, not to the inspection regime or to the certification decision, but to the original blade geometry and coating specification. The aerodynamic and thermal loads that the blades experienced in service were more severe than the laboratory testing environment had reproduced. Rolls-Royce had certified an engine against test conditions that did not fully replicate reality. The regulatory system, which depends on the manufacturer to design the tests as well as run them, had not caught this gap. In industry terms, the certification envelope had been drawn too narrowly, and operations were happening outside it without anyone realizing. The redesigned blades that Rolls-Royce eventually certified solved the problem. Today, Trent 1000 powered aircraft are flying without the uncontrolled degradation that defined the crisis years. Rolls-Royce survived. The 787 program survived. But the episode left a permanent mark on how aviation authorities approach turbine blade certification and on how airlines approach single-source engine dependencies. The broader consequence extended well beyond Rolls-Royce's own balance sheet. Airlines that had chosen the Trent 100 specifically because they valued the engineering prestige of a Rolls-Royce engine. ANA's decision was partly driven by the British heritage and engineering reputation, found themselves trapped in an operational nightmare they had no way to have anticipated. ANA alone reportedly suffered losses exceeding $200 million in revenue and additional operating costs across the years the crisis ran. British Airways, which had a significant proportion of its 787 fleet on Trent 1000 power, had to operate routes with substitute aircraft, including the older Boeing 767 that were significantly less fuel efficient. The cost differential was real and sustained over multiple years. More significantly, the crisis reshaped how major airlines approach engine selection risk. Prior to the Trent 1000 crisis, the dominant assumption in airline procurement was that modern engine programs, from qualified manufacturers, GE, Pratt & Whitney, Rolls-Royce, carried equivalent baseline reliability. A selection choice was primarily made on performance specifications, fuel efficiency, price, and relationship management. After the crisis, airlines and their technical evaluation teams began weighting engine certification methodology more heavily, specifically asking whether manufacturers could demonstrate that their real-world operational testing had validated certification assumptions rather than simply meeting the minimum testing requirements. Rolls-Royce's own certification engineers had designed the tests that the Trent 1000 passed. The tests had not been wrong by the standards of the time. They had been insufficient to reveal what the real world would do to the blades. That distinction between tests that meet regulatory requirements and tests that accurately reproduce operational reality is now a more prominent part of how sophisticated aviation technical teams evaluate engine programs. The episode also had lasting consequences for the regulatory relationship between major engine manufacturers and the CAA and FAA. The two agencies conducted a joint review of their engine certification processes in the wake of the Trent 1000 findings. Their conclusions were not publicly alarming. They did not declare the existing processes fundamentally broken, but they did result in enhanced requirements for real-world operational data reporting during the first years of service for new engine programs, giving regulators earlier warning of degradation patterns that diverge from certification predictions. Rolls-Royce did not almost destroy commercial aviation because it made a dishonest decision. It made a calculation that the blade behavior was manageable within an inspection framework. That turned out to be wrong at a scale that took years to fully reveal. The regulatory system trusted the manufacturer's own testing. The manufacturer's own testing did not fully reproduce the real world. By the time the gap was visible, it was already a crisis. The lesson of the Trent 1000 is not that Rolls-Royce was reckless. It is that in aerospace, the difference between a managed risk and a catastrophe is sometimes thinner than a turbine blade.